So, by the way, have you guys checked the attachment I sent?
Yeah, I have checked.
Okay.
Yeah, meaning I have not gone through the paper, but I've just downloaded and QSpice has been installed.
Mm-hmm. It's okay. Okay, it's okay. Don't worry because I'll try to go through this presentation together. Okay, so let me first try to share my screen, entire screen, share. So you guys can see my screen, right?
Yes,
Yes.
I can.
Okay, good. All right, so let's. Okay, I will open it here. Okay, which one is this? Corporate system architecture. Okay, so basically we have two files that we can discuss today. This is the one, and the other one is. So this is. I cannot find it here. Okay, see papers. Uh, Windows based PLL. Okay, so so okay, you guys can see the paper now, right?
Yeah.
Yes.
Hello,
Yes, we
Yeah,
can.
I
you guys
can
can
see
see
it.
that now. I'm opening a PDF, right? Okay, good. Okay, all right. So, okay, let's first start with the title here. So the title here is PLL and not filtered algorithm. To simply understand this is because in the real world, the measurement is never been ideal, right? Control algorithm, then we have to make sure that our controller can deal well with all kinds of non-ideality. So, for example, when we are trying, let's say we try to make a simulation for uh, current control converter, then perhaps in the simulation, most likely you will not see any kinds of noise. But in the sim in the real hardware, you will see a lots of noise. Or the other thing is like not just the noise, but you also will have some issue with the offset as well. So one so for example, if you want to transmit, let's say 1 amp, but your sensor have like an offset of zero point 0.1 amp. So when you are sending 1 amp, actually you will send 1.1 amp to the system, this kind of thing. And in general, if you're talking about a DC to DC converter, then offset normally is not a big issue unless in terms of the control performance, unless we are talking about like we need to make like a metering for the billing purpose, then we have to make sure that our measurement is correct. But from the control perspective, then there is no issue there. Okay, so basically, however, for the PLL, it is pretty sensitive against noise. So that's why when I realized that in my measurement I had some kind of weird issue, so and then this issue causing my measurement to have pretty significant offset. So then I decided to, okay, I'm not going to fight this offset, so I just live with the offset and then find some algorithm, some PLL algorithm that can deal with this DC offset properly. Because for most of the PLL, if unless you are specifically looking for the PLL that can handle DC component like this one, then your PLL will have some oscillation on the estimation output. Okay, so basically here what I like to present is, so this is a paper that I'm going to use, and then I try to compare some of the methods that I can find on the internet. So the first comparison paper I found is the one that I found in, where is it? Yeah, if I'm not mistaken, should be this one. Not this one here. Where is it? PLL via face design tuning power PLL comparison. This one. Not this one. Okay. So there is another paper that I've originally tried to study, and then when I in my design principle, I always try to just in something that is as simple as possible. Okay. So, for example, this algorithm, uh, I only need like, let's see how many lines. So I already do this, but in a different simulator. I do not use QSpice anymore for my project, because in the QSpice it works well, but it needs some extra effort there. So I do not really like to do it anymore. So let me see which one is which. PFCPWM modified PLL. Okay, let's just open this one. So here basically we can see that, yeah, yeah, thank you. This whole PLL algorithm can be implemented in just the PLL itself. It's just this line only. Sorry, from the paper it's just this line. But then there are some other modification that I did as well. So yeah, it's not as simple as this one anymore. So is there any questions so far?
No.
No. All right.
Okay.
So okay, so this then next point is we can try to discuss about the logical process on how we can move from the original block diagram that we can find on the paper, on the reference paper, and then how we can modify the algorithm into something that is more useful for me, or something that suits better to my need. Okay. So for example here, uh, we can see that this is the original structure that we can find on the paper. However, then after some thinking, then I can modify the structure into this structure as this one. So what is the, okay, so next then I can explain what kind of modification that I did, so to, to better suit my need. So number one is, in many papers that discuss about the use of a single phase PLL, almost all of them only use a normalized input. So basically, normalized input means that the peak magnitude of your uh, single of the sine wave measurement must be normalized to one. So for example, if you're working with 220 volt grid, means your peak voltage is around 310. So you have to divide your input voltage uh, by 310. So then your input can be one. Okay. So, however, uh, technically speaking, for the actual implementation, generally most of the PLL algorithm that you can find in the literature that can work with not exactly one, not exactly with an amplitude of one, but they normally can work with pretty, like, let's say from a zero point 0.5 to 1.5. So in the algorithm that I implemented, basically the first step of the calculation will be to scale down the AC sine wave measurement into some normalized value. And then for the normalization, I I selected this 110 multiplied by square root of 2 multiplied by square root of 2 means, or actually same as 1 divided by 220. Okay. And The specific reason why I chose this number is because we know that the input voltage, the generic uh, worldwide input voltage is around 110 up to uh, 220. That is pretty much a general input voltage that you can find in almost everywhere in the world. So number one thing, the first thing that I need to do is to calculate, to convert the 110 and 220 into the peak value. So let's say this 110 volt RMS, so the unit is volt, sorry, the unit is volt RMS. So then first part, I have to convert it into volt peak, right? So for the 110, it means equals to 110 multiplied by square root of 2. And then the same for, sorry, and then the same for this one. So this one will be 220 square root of 2. So basically our uh, normally for to normalize the input voltage, and we can divide by this either of these two value. And then the next thing is, so this is where we get the first square root of 2. And then for this divider here, I have the second square root of 2. So the reason why I have the second square root of 2 is because I want to find like somewhere in the middle between this voltage and this voltage. And there are two ways that we can do to find the middle point. Number one is we can take the average or the mean. So the mean is basically it will be just this one plus this one divided, yeah, divided by 2. So it will be 233. Or we can take the geometrical middle value between the two. So basically we know that 311 is like 2 times of this one, 155. So if we want to take like the geometric, uh, like the middle point geometrically, then we can also like do this geometric middle. I don't know how to call the scientific term for this. Let's call it geometric middle. Then we can do this. Uh, this one, 110 divided by square root of 2. Square root of 2. So the reason why we can choose 311 divided by 2 is because if we take this, if we try to make the normalization, okay, so so now let's make this normalization case with these two, like the mean and also with the geometric middle. So if you take the mean and then we take the normalized result, then for 155, so for 155, then the value will be this divided by this one. And then the other one, for the normalized result, it will be equals to this divided by this one. Okay, so if you take this mean, then the range of our input signal will be in the range of these two values. However, if we take the geometric middle, then the normalized result will be this divided by 220, and then equals to this divided by this. Okay, now, so what is the difference between these two? The difference is for this one, okay, uh, generally, actually, this one, the distance between the actual value here compared to 1 will be farther than compared to this one. So because this one, if you take the the ratio between this value to 1 will be, this one will be following the linear step, but this one will follow the geometric step. Both of them are generally very similar, but in my understanding, because for the the behavior of the controller typically follow more closely regarding to the geometrical uh, order. So that's why I prefer to choose this using this geometrical middle for the normalization. And 220 is also a number that is easy to remember. Okay, any questions so far?
Just this geometric mean you're using because you want the system to be useful for both 110-volt system and 220-volt system, or
Mm-hmm, mm-hmm. Yeah,
if
correct.
it is only
Yeah,
for 110-volt system, then you wouldn't require this, right? Or if it is
yeah, of course.
set.
You just choose 155, for example, in such case.
Okay, 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 okay. Yes.
Yeah, so mhm. Because you know when because actually using this one for my work project, and then in the power supply company when we design something, we almost always talk about universal input. So yeah, this is kind of a
Yes.
big deal.
Okay.
Mhm. And then the second part is uh, okay. So if it look like in a simple manner, you may see that my diagram here is a little bit more complicated, right? But actually, it's not really that much more complicated. Okay, so number one is in this diagram. Okay, if you look at this section 6, you will see that. So in this diagram, it has a few constants. They call it mu0, mu1, mu2, mu3. So in this section 6, then you can see the value for mu0, mu1, mu2, and mu3. So mu1 and mu3 is basically the grid frequency to 550, or yeah, grid frequency where they live. And so basically, um, for the mu1, mu3, it will be grid frequency, and then for the mu2, it will be like the controller gain. Okay, so now let's first talk about mu1 and mu3. So basically, because mu1 and mu3 are the grid frequency, okay, and and somewhere in the paper they say that this structure is similar to a band pass filter. So if we want to make sure that our system can operate optimal in wide range of the frequency, so we have to make sure that the central frequency of our system is at the grid frequency, right? So in order to ensure that, then the simplest way is to remove this gain. And so for the mu1 and mu3, I remove these two, and then I replace it with the multiplication. So and then I multiply this this input here with the frequency estimation. And of course, I put a little bit of low pass filter to make sure that this uh, gain doesn't change like uh, erratically, because if the gain here change erratically, then our system may become not really stable. Okay, so this is the second change that I did. So basically, sorry. So basically, eh, eh, is that anyway? Okay, and so yeah, so basically the second step is I replace the gain with the multiplication, and then I take this, I multiply it with the estimated frequency. Okay, and then there is also this uh, mu zero. So for the mu zero, basically in this paper, they already provide like this kind of diagram to compute the relationship between mu zero and the grid frequency. Okay, so then we can simply follow this. And as you can see here, for the mu zero, generally speaking, it doesn't vary too much with a different grid frequency here. So actually, it don't have to be very precise. You can choose here, you can choose here. It will not have very significant effect because in the controller, typically when you change the gain like only by, let's say, plus minus 10%, your system should not be affected significantly. Okay, and then the next part of the equation is the, here is there is this mu2 here, and then for the mu2, they in the paper they already presented uh, this formula to calculate the mu2 to so there is the mu2 equation 12. So yeah, so in the paper they already made specify about this. Okay, and so for the mu2 we can, number one, they have this relationship, and so from this relationship then I can compare this equation with the generic form of the second order equation, and then I can adjust the damping ratio to the value that I wish. So here I have this formula here. So from the paper you can see that they already provided this thing. Okay, and so what I need to do is I compare this with the generic form of the second order system. Okay, and then in this generic form of the second order system, basically when we design a controller, if we want our system to be like to have good transient performance, one thing that we can really modify is the damping ratio. So it is common for us when we are designing a controller, we want our system to have damping ratio of somewhere around zero 0.5 to zero 0.6. So the reason why we want the controller, the system to have this amount of damping ratio is because if our damping ratio is very high, it goes uh, very close toward one, then our system becomes a little bit sluggish. It becomes like slow, not responsive. But if the damping ratio is very small, then our controller becomes like the transient response will be like it may have very high oscillation. And uh, so this damping ratio of around zero 0.5 to zero 0.6 is the reason why we have this phase. For example, if you design the controller with in the frequency domain, you will see that the general recommendation for phase margin is somewhere around 45 degree or higher, higher than 45 degree. So because the phase margin is in is basically like it has very close to linear relationship with damping ratio. So roughly speaking, if we are talking about damping ratio less than zero 0.6, so if we have this relationship for damping ratio less than zero 0.6, okay, then basically the phase margin damping ratio of in the system can be approximated as, sorry, it should be like this, approximated as 100, sorry, phase margin divided by 100. So that's why if our phase margin is, let's say, 45 degree, then our damping ratio will be close to 0.45, roughly speaking. If our phase margin is around 60, 70 degree, let's say 60 degree, then our damping ratio is around 0.6. Okay, so in our, for us, when, for me, when I need to tune this new tool, okay, then I can use this formula, and then for the damping ratio here, I can choose 0.6. So that's how I get this. Uh, that's how I can calculate the new formula here. Okay, is there any question? Any question? Any question?
No, it's
Okay, sure. All right, and then lastly, the last. Oh, sorry, not the last actually. There are a few more. So the next modification. Okay, so if the input I normalize with this value, so for the magnitude estimation, yeah, I just need to inverse this. I multiply the estimated magnitude with this the same amount of gain, so I can get the estimated output. Okay, and then in general for me when I'm using this estimated magnitude in the controller, I don't need it to be very responsive because in practical system the output voltage doesn't sorry the grid voltage will not change that rapidly, so I can apply a lot simple low pass filter here to smooth it a little bit further. Okay, and then the other thing that I do is here. So does anybody understand what does this mean? What does this block actually mean? Anybody want to try?
Is to convert
Anybody want to try?
the to AU
Sorry. So
to convert
originally it was
to the PU units, I think.
uh-huh. So basically this is okay. In the original paper, okay, the way they write it is like this. So so the frequency estimate is equals to this integral output and plus this omega zero, right? Now, so mathematically speaking, because we know that when we want to do an integral, we also have to define what is the initial value, right? And actually, if you think a little bit carefully, this kind of offset here, like this, yeah, some kind of uh, omega zero value here, basically will behave exactly the same as the initial condition. So if you do not if you do not add this term, okay, then the value of the omega here will start from zero. But why should we want to estimate the grid frequency from zero? Because practically speaking, the grid frequency cannot be anywhere near zero, right? So uh, in my case, because we want to make the system to be able to operate between 50 and 60, so I can take the initial frequency estimation to be between 50 and 60 hertz. So that's why here I use 2555. And then I, I modify this plus, I modify this plus plus into initial condition because then practically speaking, they behave the same. Okay. And then lastly is in the practical programming, you it is not a good idea to have unbounded integral because if you have unbounded integral and then when something goes wrong, then you can have something called overflow. So overflow is basically a condition where your uh, the number in a variable goes beyond the maximum number that can be uh, quantified by the data type. So, for example, simple example, if you are working with a 8-bit integer and then the number is uh, signed, then you can the number that you want to put there cannot be greater or smaller than plus minus 127. If you try to write, let's say, 127 plus 1, what will happen on the computer or on the microcontroller will be from 127, the next part will go to negative 127, 128. So you will have this overflow problem. So in order to avoid that, it is uh, much wiser if we add integrated clamping. And then the other thing is the reason why I chose these two value 65 hertz and 45 hertz is because for most grid, it is not practical to go beyond that value because let's say you are working in a 60 hertz grid, then practically speaking, if your frequency goes beyond 60 plus minus 1, then the whole system should already shut down. So yeah, we don't need to have very big value. Okay, is there any question? Any question here?
No, just 65. It can also be like we can keep 62 and 48, something like that also.
Yeah,
I think you're meaning the
yeah,
anti-aliasing
technically you can.
requirement, right? Or I no, I think power
Yes,
quality, like
correct.
plus minus 1 hertz. Some this thing is there.
Mm-hmm, correct. Yeah.
So, like, is it
So
required up to 65, or we can keep up to 62 or 48 like that?
I'm not really sure, but generally, uh, the our algorithm should be able to handle like the craziest combination.
Okay.
Yes, technically you can set it at 62 only. That should be fine. But I think the other thing is when you are setting like a controller like this, because this one later it also connect to like the frequency estimation controller, right? So when you set a controller, it is better to have some small extra margin for your control variables to go. So for example, yeah, technically you're right that the maximum frequency should be, let's say, 61. But if we make the climb at 61, then actually our controller will be a little bit slower to reach 61
Okay.
in case the grid is really 61. So that is my current understanding.
Okay.
Mhm. And then the last thing is, of course, when we have from the omega, when we convert into theta, then what we need to do is we need to do integral, and then for our integrator, we also have to have we have also have to reset the value every time the phase estimation goes beyond 2 pi, because the computer will be very slow to compute bigger value. For example, you, in the MATLAB, you can calculate like 10,000 pi, the sine or cosine of 10,000 pi very quickly. But I think in the microcontroller, you will with extra computation cycle if you want to calculate 10,000 pi. And actually 10,000 pi also pretty much meaningless, right? So you, it's better for us to always reset like this integrator. Okay, is there any question? Okay,
No,
if
no, not
not,
from my side.
mhm, okay, if not, then the next thing that we may be in the, that I forget a little bit is basically this PLL will have four part estimation. Number one is the output, the grid magnitude, the frequency, the phase angle, and lastly is the DC component. Well, how much is the DC being stored on the measured signal? Okay, and somehow when I'm looking at this, I'm thinking about, for the PFC controller, it is typical that for the PFC controller, the DC link controller, that the voltage output voltage controller will have very low crossover frequency, because the idea is they want us to prioritize to have good input current harmonic, and we can sacrifice it with letting the DC link component to have big sine wave oscillation at the double of the grid frequency. But in order to do that, typically the way we do it is by using very low crossover frequency for the voltage controller. However, the downside of working with a low crossover frequency is if you have sudden large load transient for your PFC, then your controller may respond very slowly. And some of the tricks that people use to alleviate this problem is some people use like a notch filter in their controller, so that the controller can be designed so that the controller will not react to the 100 and 120 hertz DC link ripple, but you can still set the you can still set the controller crossover frequency to be at higher point. Let's say it is typical for most TFC to work with around 2 hertz to 5 hertz crossover frequency for the outer voltage loop. But if you are using a like a notch filter, you can push the crossover frequency to, let's say, 15 hertz or 20 hertz, because your controller will not react to the ripple. It only reacts to the DC level. And somehow when I'm looking at this paper, I'm thinking, oh, maybe I may be able to use this PLL algorithm on output voltage sensing of the PFC, and then I can just use this DC estimation for the DC link controller. But yeah, that's an idea. Okay. All right. So yeah, basically this is it for the whole algorithm explanation. So now let's try to explain about how to implement this in programming and also in the QSpice. Okay, so this is start from 0. There's nothing here. So number one, that I will try to save it first to make it easy. Let's just put it on the desktop. Where should I put it? Desktop, 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 desktop. Look in the folder. Anytime. Okay, so number one, I can set a voltage source here. So in order to show a voltage source, you can just press a letter T in the QSpice, and then you can put a ground here. Okay, you can press letter G, and then you can connect the two, and the shortcut for that is you can use a wire to connect the two components. So the shortcut will be W for wire. Okay, and then here we can adjust the parameter of this voltage source. So in this case, then we to make it simple, we can just simply use a sine wave. So we can write sine, and then here it gives us some suggestion on some guidelines on how to write this voltage source, how to configure the voltage source. So number one, we have offset, magnitude, and the frequency. So let's say the offset is 5, the magnitude is around one, let's say 155, just for fun, and then the frequency is, let's say, 50 hertz. And then next we can write a little bit of wire here, and then we can put the label on this net. So the way we can put a label is we can uh, press letter N on the keyboard, and you will see this question mark, and then we click on this net and this wire, and then we can double click on this question mark, and then we can say, like, I don't know, key sign, example. And then in order to run the simulation, we need to create a spice, or a directive to tell the spice on how we want to run the simulation. So we can first press dot on the keyboard, and then after that we write the spice directive for this. So for this one, we'll be running a transient simulation. So the tan, and then first part will be ignored. We follow the second line. First part will be ignored. Like normally just write the 0, and then t stop is how long we want to run the simulation. So just to make it easy, we can say 1 second. So just like one. This stop is when should we start to save the simulation data. And just write 0. And then next time set is maximum simulation time step. So for this one, because this one is going to be not something too fancy, so you can just set at 5 micro. You don't have to be very quick. And then in a power electronic simulation, unlike a linear analog simulation, uh, power electronic is very difficult to estimate for the simulator to estimate the operating condition of our power electronic circuit, because power electronic is basically switching circuit. And however, for analog circuit, it is a linear circuit. So the somehow some people who are very smart who develop spice, they can develop an algorithm to estimate the operating point of the circuit. So in the power electronic, it is generally recommended for us to have the UIC at the end of the transient directive. So UIC simply means uh, uh, basically we can tell the spice to just skip the initial condition estimation for the simulation. Okay, because it is not uncommon for people when they are using the spice for switching converter that the estimation is wildly wrong for this initial condition. Okay, so now we just run. We just see what the where are you? We just see what this result looks like. Where is it? This one here. So we just have this sine wave. Okay, so here we see that on the to show which waveform we like to see, we can just click it on the screen. If we want to see the voltage, we can click on the map, and then if we want to see the current, we can click on the component. Okay, so here we can see that the voltage is like this, and then on the graph, you can click on the graph, and then if for me, I much prefer to have grid to to understand the plot a little bit better. So on the screen here, after I click this uh, waveform panel, that I can press Control G to enable the grid, and then we can zoom by dragging the screen, making this rectangle by clicking your left button on the mouse, and then just like this parameter here, this one says that it has 5 volt offset, so we can see that the the value here is the bottom is 150 negative 150, because yeah, minus 155 plus 5, and then the peak here is where is it, 160. You can see at the bottom there 160. So it this is correct that the voltage here have some offset. Okay, so is there any question so far?
No.
Okay, we can move on. So yeah, that was the easy part. So now let's move to the programming part. Okay, if you don't know how to do the programming part, so basically in the QSpice it supports the C block. Right. So to make the C block, we first need to do this: draw hierarchical entry. Okay, you right click on the screen, and then you choose this draw hierarchical entry, and then you just draw one block basically. Then it direct automatically make you this one, and then you have to enable the option for this block. To open the option, you can press F3 on your keyboard, and you will see this option. Okay, and then let's make it bigger. And here we can see that there are a sorry, and here we can see that there is this thing called a symbol type. So for the symbol type, you can choose this, I don't know whatever this symbol called, but yeah, this is a .dll. So it means that we want to tell the QSpice that we want this block to have a compiled code, which is in this case it will be the DLL code. Okay, so here now after you enable this into .dll, now when you right click here, you will see this option C++ interface. Okay, and then later we can create a C++ template. By the way, before doing that, we first now can add a few ports to tell what is the input and output of this block. Okay, so now here we can just add port here, because this is just a simple PLL, so we can just have one input only. That should be sufficient. Okay, so we can tell the spice that this port is an input. Okay, And then here you right click again, then you can choose a data type. So what kind of data that will be parsed from the QSpice into the PLL. And for this one, basically you can choose it as a float or 64. Actually, this is called double, and the more general programming term, because this is a 64-bit variable, and typical float is only 32-bit. Then here we can, I I can click this one, the left button here, so that it will align better, and then we can call this like P sense or wait a little too long, PAC should be enough. And then next we can create the output, what we want for the output of this block. So for example, number one, I want to see the so based on this block, let's say, okay, the first estimation that I would like to see is the voltage magnitude, and then I want to see the omega, the theta, and then the omega after filter here. Okay, and then what else? DC voltage, yeah, basically all of those. Okay, so let's set the name one by one. Okay, data type, double. Okay, so for this one, let's say this one will be the P. Okay, I call it magnitude for magnitude. Okay, next will be copy, copy. Control copy, control V. You can just hover on this thing and then you can press control Z and control Z. And then next, uh, sorry, for this one, let me check. This one should be port type should be output haven't selected, and then the data type is float. Okay. Here, the port type is the output, and then the data type is float. So, okay. So number one, we have the magnitude. Okay, and then next we have the magnitude filter. That's for fun. LPF means auto low pass filter, and then after that we can get the DC value, DC estimation, and then we can get the frequency. Okay, let's say the okay, let's call it like so. Before showing up, then we will convert from the radian per second into hertz later, and then we can have the frequency of the filtering. It is IPF, and then after that we can get the theta, th. I know I just call it th. Okay, and then after this, the next thing we can do is we can tell the QSpice to create us a C code template. And then normally for me, I can just choose this one. And then QSpice has this rather unique feature. So in the QSpice, Mike, the creator of this QSpice, he decided that the QSpice, the C block can be designed, is designed so that it can manipulate this overall simulation sampling time. Okay, and for this example, I use this feature to optimize the simulation for a switching converter, because I can use this to make sure that the simulation do not need to waste too much time on something unnecessary, but can directly go to the actual switching event. Okay, but for this particular example, this is not necessary. Okay, and then there is also this trunk. So trunk is basically like we can tell the simulation that how much is the time step that we can allow. Sorry, we still need to use this maximum external step size, because we can use this to make the sampling trigger in the simulation. I will show you how I do it later, but we don't need the rest of the options here. Okay, so let's say okay, and then it will automatically create this file, and then you can find this file directly at the folder. There is University PLL here on the same folder, you'll see this uh, C code that is generated by the QSpice. Okay, and then before we go any further, next thing is you can simply compile and run. You can press F5, or you can just right click on the anywhere on the screen here, and then you can just compile PLL and run. So for example, now before I do anything, I can just compile it and run. And oh, it says, okay, this is the singular matrix. This reason why it has singular matrix is because this port is defined as an input, but the input is not connected to any there. So the Spice is confused. Why is my input is open? So, so what can we do to solve this one is simply we can connect this AC to the sine input here, and we can rerun this simulation. Just press F5. Now, obviously, we do not write anything here. So if we try to press any of this, and we will not get anything output. So in the simulation here, just to prepare for simulation a little bit easier, to make the simulation to be a little bit more organized, we can make all of this have a name. Okay, so here we can connect to a wire for all of this. Okay, and then sorry, we can and we can set the name here.
Hi,
Let
Arif.
me
Actually, I just missed that.
oh sorry,
Sorry to interrupt.
yeah,
I just missed like
yeah, so yeah,
after
but
making
your
the
voice
blog.
just sold out. Sorry, yeah, can you say again?
Yeah, just
Suddenly your voice is super
how do
loud.
we make that C code block, right? I just missed like I made that thing with all the names, magnitude, LPF, and all.
Okay.
But when I'm double clicking it, for that
Uh-huh.
coding part, enter schematic should we press
Oh,
or
you
what?
cannot double click.
Or I mean, right click basically,
Here, you
enter
right click
schematic
here.
or
Okay. C++
and
interface. Oh yeah, you right click
which
on this block. You right click on the block.
okay.
You right click on the block
Then
here. Right click on the block, and then you see this C++ interface.
okay, I'm not able to
Do
see
you see the
that
C++
actually.
interface? Oh, have you changed the
Um,
symbol type? So do you see this screen on the right here?
okay,
Symbol
yeah. That
properties
I'm
of
seeing.
the drive.
Symbol type I did not change, I think. Yeah. Can you zoom a bit
Yeah,
to
you
that?
have to change it into .dll. So here there are many, but basically you just choose to .dll. I think I cannot zoom it, but you can try to find it.
Okay, dot DLL.
It's
Okay.
somewhere in the bottom. Yeah,
Okay,
.dll.
okay, 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 okay. Then I think I missed that part. Okay, dot DLL I got. Then
And then
okay, now I'm getting C++
now when you
interface here. Yes, open
yeah,
C++ interface, right?
so now yeah you see the C++ interface, and then when you by the way when you add this all of this how to say it, the node here like the port here,
Okay.
you have to make sure that you set the port type as an input or output, and also set the data type as a float or yeah whatever you need.
Okay, I can't just. Can you zoom a bit in that side attribute? I missed that part.
I cannot zoom, sorry.
It's
So I
okay.
just wait here. So here.
Like VAC and net name is V.
So yeah. So first you
N01
okay.
something is written, right? Magnitude what is
So again,
written
I
there?
can make. Oh, so okay. For the manager, so for the VAC here, okay, the port type is input, the data type is float. Okay, and then on the right here for all of these, basically, the port type is output, and the data type are float. That's it.
Data type
And
is
do it anytime. Float.
float. Okay.
Yeah, float.
And even input also it's same, right? I mean, port type is also have to put input, and data type
Correct.
everything is float.
Correct.
Okay, okay, fine, fine.
Okay, so now I can just rename for each one of them, make the name here because later when we try to plot this, um, the plot viewer will show this name. If I do not set a name, then they will just put some random name that will be a bit difficult to understand. Okay, so here. So this one is still busy, and frequency, frequency LPF, then lastly is n theta. Okay, all right, and so now we can start to write some code here. Okay, so the first thing that we need to do when we write a code is we know that in our microcontroller later, our PLL will run in a discrete time manner, right? So when our code will run in the discrete manner, then in our simulation, we also have to simulate the controller or the C block with a discrete manner. Okay, so to do that, then we have to introduce sampling in our um, C code here. Okay, so there are many ways to do this, but the my favorite way, like the simplest way that I often do, is just like this. So oh yeah, by the way, I haven't used QSpice for some time, so my QSpice knowledge is maybe a little bit rusty, but let's see if I can, if this trick still can do. If t is greater than the t sampling, yeah, like what? Sampling time. Okay, let's just call it sampling time. So how to call it? Okay, if sampling, then we will do some algorithm. Okay, and then if t is greater than t sampling, okay, and then here, basically, the way we can achieve the sampling is by making sure that the the okay, it's a bit difficult for me to say. So now we have to explain this that we want to add some variable here. So we call we can add some variable in this structure where we will store the data. So we can call it sampling. So this sampling will be like when we want to run the sampling in the next period. Okay. So if t is greater than t sampling, then we will run some algorithm. So before we do to any of the more complicated programming, now we just make a simple counter that run every, let's say, 10 microsecond. Okay, we just choose 10 microsecond because uh, it will be simple and pretty like commonly used frequency. So let's say the sampling frequency is 100 kilohertz. So now we just do something. We just need to do this. Make plus plus. Okay, so ideally every 10 microsecond we will see that the output change, but it will not change every time. Okay, so basically after here we can say that once we hit this point, oh, this one should also include equals. When we reach this point, then we can move the next timing target by the sampling period that we like. So will be 10 microsecond. Okay. So that we can do this and we can plot this one now. Okay. And then this is the last thing. Oh, sorry. One more thing is we need to store the previous simulation value. Oh, apologies for, oh, all right. No problem. Okay. So the next thing is we need to store the previous simulation time. So we can say that normally I call it like ttref. So here double ttref. So this is will be the previous the current value of the time. So here I can store this value into this structure ttref equals to okay. So here basically I can simply return the the instance sampling minus instance of the tpref. That's it. Okay. So now I just have to save Control S as usual, and then next we can just compile and run. Let's see. I hope this one doesn't complain. Okay, it looks like it runs. Now we can check the value of the Mac. Okay, it increased, so the counter works, right? And then we can check how often is this uh, increment run. Okay, yeah, sorry, not that confident sometimes. Okay, zoom in. Okay, okay, so here we see that from the 0 to 100 the value is constant like this, but next the value is always increasing, so pretty sure something is wrong here. Okay, so yeah, I will, let's take a look at this part a little bit later, but now we'll see what else that can, that maybe go wrong. Yeah. Eh, okay, yeah, one of the things that I do not like about QSpace is you cannot zoom out. That's okay, just try to enjoy it. All right, so let's see. Oh, sorry, this one is wrong because this sampling minus t prep. Hmm? Oh, it doesn't make sense. Let me see. Let's try to see it a little bit smaller. It gets bigger. Okay, doesn't make sense. So basically now in here the sampling process doesn't run properly because yeah, basically just over the like the accumulator just way more active than what it's supposed to be, right? So let's see what is not correct here. In the pt track equals to p. If p is greater than this sampling, then this sampling will be equals to this sampling passed to the 10 microsecond. Okay, now let's try to compile it again. Let's see how does it behave. So if it works well, it should look like a staircase. Oh, yep, it looks correct. So here we can see that at the 10 microsecond, the counter increased from 1 to 2. Every 10 microsecond, the counter increased by 1. Okay, so basically from here we can validate the sampling process has been done properly. Okay, is that the question here?
Actually, I just tried, but I'm not able to. There's some fatal error showing actually. Could not find
Okay, you
EPLL.
have
Dot. Is it somewhere else
a
you should say?
fatal
Or
error. Okay.
could not find EPLL x1.dll.
Oh, have you compiled? If you press this compile and run, you can right click here, compile DLL and run.
Okay. What's that?
Does it work?
Compile.
And run.
Okay, there is some comma somewhere. I'll just check once.
Mm-hmm. Yeah. So basically, we should take a break at 9 o'clock. So like in 10 minutes. So now we just rectify this thing before we take a break, and we will continue with the rest of the whole algorithm after the break. So now we just talk casually. Does it work now? If not, I can try to copy and paste the whole code
It
to.
is some sort of
But
error.
by the way, I cannot really copy.
T greater.
Okay, I will. So at 9 o'clock, let's take like 15-minute breaks. Okay. Let's take at 9:00 to. Oh, T is sampling and it explicit. Oh, you forget. Okay, you should write it like this: if v greater than or equal instant sampling, and then you have to use this like minus and then this right bracket.
Okay. There it is.
Because here what you did is you compare and compare again.
Okay, okay. I just missed that minus. So, okay, okay. So it's actually not showing any line basically. Like it's showing error in line 75, but I can't see the lines. Is there any way?
It I understand what you mean, but this is the crappy thing. If you don't like it, you can copy the code, put it in the Notepad plus plus, and check the line number there. Yeah, I agree with you.
Okay, you
Or
put the
actually, you
code.
can click. Uh-huh. Sorry,
No, you
or
put
you
the
can
code somewhere.
no. I just put it here. I don't know do anywhere. Just double uh, zoom out. So actually, the one of the little bit stupid way to check your line is you can click on the code and then you can see on the bottom here it says what
Okay,
line
okay,
is it.
okay. Okay.
Yeah, this is the like the annoying thing about this editor. So if you so for me when I write the more complicated code, I will copy the code, put it in the notepad plus plus. So I like to do this
Okay.
copy notepad plus plus and yeah paste here and I just use a language C and here I can see yeah what line is which.
Okay.
So this one also do not have any like we cannot really see where how long is the bracket goes, so it's not really nice.
Okay.
Yeah. Okay. Anything else?
Uh, sorry, Mr. Arif.
Sure.
Yeah, suddenly your voice is
Oh.
smaller than before. Your voice,
Really? Oi.
yeah, yeah, it's better.
Better now?
Yeah,
Okay. Sure. Thank you. But if you don't have any question, you can just leave. If you still have question, then I will wait until 9 before I also take a break.
yeah. For me now, for me no.
Hmm.
For
Okay. Yeah. So if you don't have question, you can take a break and come back at 9:15. But Sachin, if you still have question, then I'm waiting for you until 9 o'clock.
yeah,
Sachin, does it work now?
Actually, there is some comma colon missing, but I can't find it actually. Somehow it's there. I put
Okay.
everything, but this is what it's showing, but I can't really find any issue. This.
Okay. Yeah. sometimes when you do programming, you have to like have very good
Ah,
eyes.
correct, correct, correct. I'm
Okay.
checking in laptop. Okay, no problem.
All right.
I'll do it.
Let me try to
Identifier declarator mag plus plus. What's that?
try. Eh, not deleted one. So some people complain that I use var, so I just use a zip one. How to send it to you? Okay lah. I'll just spam the Google Calendar invitation with this email to anyone. Email address, I guess. First part of code, and then I will just say, so to help you later to join, if you give up, you can open this file, okay?
Okay, okay.
Okay, thank you.
Okay, later we will continue. Okay, now I will take a break. You can take a look at that one. It works. And by the way, I do not send the .dll because .dll often uh, misdetected as a virus. So you can open the QSCH and then open the C block and then you compile yourself. Okay, talk to you later.
Okay.
Hello, hello, I'm back.
Okay, let's go.
Is it back? Okay, let's go. Okay, so Sachin, are you here? Taufik, are you here?
Ah, yes, yes.
Okay, Taufik, are you back? Okay, I assume you're back. Okay, so Sachin, you can open the my email, right? And you can compile it, right? Hello, hello, Sachin, Sachin. Okay, fine. So now the next step, we where is it? Where is the sheet? Okay. So now we can already make this sampling, right? Is to make sure that our sampling works, so we can read the input and send it to the output. Okay. So yeah, we just modify the code a little bit. So if before just to read the to just like make a counter, now we can modify this counter to just simply make equals to PAC. So we just copy the measure input into the output. Okay. So we can press modify it and then press F5, and here now it's plot, it shows us the magnitude result, and then we can compare it with sine wave. What is the difference between the two? From far, it should be same, but if you try to zoom it very closely, we can see that now the value that the block reads, the algorithm reads, is sample becomes like this. Okay, so this is the difference. So sorry, basically what the algorithm does is simply that uh, every time you hit the sampling point, okay, then you will read and update your, then you will read the input value. So then it looks like this, and then between here and here you do not do any reading, so your the value in the C block stuck, right? So there's no update during this point to this point. So this is the sampling. So now we can sample the input. All right. So now, sorry, I just had dinner, so my throat a little bit messy. So all right. So the first part we can try to do is we can do this uh, the normalization, right? So number one, what we can do is we can sorry we can add a new variable, all right? So the new variable here is we can call it double um, sorry VAC normal normalized, okay, VAC normal. So all right, so for us to make it a little bit easier to notice the difference where the code start and then code end, so I like to add this kind of marker here, so it will be very visual for me to notice where the code start and where the code ends. Okay, so now we perform this normalization. So VAC divided by 220. Okay, sorry. We have to put this value into this variable. So we can call it like instant VAC underscore normal equals to VAC divided by 220. And then if we want to plot it, then we can just say max equals to instant VAC underscore normal. Can do this. Now we can press right click, compile PLL and run. And hey, where are you? Now it becomes like this. So we can see that now the value is just becoming very very small, like this as 0. I don't know, around 0.7 something. Okay, so we do the normalization. Right, so after normalization, next we will need to compute the error, and then for the error we have to compare this. We can compute the error based on the sampling value, the normalized value here, negative minus this DC component and minus this value here. And for this one, we will call it Y. Okay, so the error equals to sampling, the normalized sampling minus Y minus DC. Okay, so now we can make a new variable here, call it error, for example. Okay, error equals to VAC underscore, sorry, instance of the VAC underscore normal minus uh, DC. So we will, and then the other one is Y. Okay, so number one is minus Y minus instance DC. Okay, so we will write the other variable here as well. Okay, double Y double DC. Okay, so now because there is no calculation for Y and DC, so if we try to run this and plot it, so now let's say for example we plot the error into the Mac output, so we can do this, then the value should be exactly the same as before because the error and Mac is not there. There's no calculation for those two yet. So yeah, pretty much similar to before with the sampling and everything. Okay. All right. So now in here, basically we can split the whole algorithm into three branches. This is the first branch, and then this is the second branch, okay, and then lastly this is the third branch, okay. All right. So now the first thing first, we just because this is the easy thing, so we can first calculate what is will be the DC estimation value. Okay, so this is the error. So when we write a control, when we write an like, okay, let's call it like a control algorithm. We know we almost always start from the left and then we will end at the right, typically. Okay, not always, but very likely. And then for the mu zero, because it can just follow the value on the paper here, 85. So we'll just multiply by 85. Actually, it will be a little bit lower because our estimated frequency is somewhere around here because 50 hertz is 340, and then for the 60 hertz is somewhere around 380 radian per second. So somewhere between here and here. So we can, okay, so actually we can also just choose 80. So now we can compute the DC value. Instead of the DC equals to, okay, and here we have this integrator, right? So integrator, if there are many ways to implement, there are a few ways to implement integrator. So the sim the if you want to say like the most mathematically correct, you can do the trapezoidal rule. However, because our sampling rate is much higher than the fundamental frequency, like the 50 or 60 hertz, so we can just use what's it called, like the what's it called? Not triangular, but like a zero order
Backward
integrator.
Euler and forward Euler something.
Sorry. Oh no, no need
Backward
to go
Euler.
that far. No need to go that far.
What?
Zero order.
Okay.
So basically, zero order means like you assume, you assume that, okay, let's say you want to make an integration of this in this curve, right? For the trapezoidal rule, you assume that the value between these two are like a straight line, right? However, for the like the zero order, you assume that the value just stuck at this point from here to here, and this is valid for as long as your sampling rate is much higher than your frequency of interest. Okay, so for the integrator, you just need to write this because the DC is after the integrator, right? So DC equals to DC. Oh, okay. To make it a little bit easier, I can write it like this: DC plus, uh, let's say the mu zero here. I want to set it as uh, let's say 75. How much is it? 80. Sorry. Let's say for this mu zero, I will set as 80. So I will just write 80 multiplied by the error value, okay, error, and then multiplied by the sampling rate. Okay, it's a better programming practice to simply write the using a define ts, and then I could say -6. Okay, or yeah, I can just leave it like that, ts. Okay, so here I can replace this e to the minus 10 e minus 6 into ts, and here I can multiply with ts. Okay, so then basically this dc will be like the integral of this thing. All right, so this is the integrator. Okay, no question. I hope there is no question. Is there any question? Is there any question on this
No,
part?
no, no, no.
So okay, so we can just implement it this way. Okay, let's put it like this. Okay, so that is the DC value. Right. Next, we will compute these two things. All right. So uh, why the middle line here, the middle block here will be computed last because for this one, we will need to get this theta. Okay, so it's better for me to calculate the bottom part first to obtain the new theta and also the new sine wave so that we can calculate the y value here at the end. Okay, so sorry. So next we can compute this part. Okay, the middle part, the bottom part here. So for this one, we can see that, okay, here in the code, we see that for this thing, we we have like this sine and cosine value, and then we use it more than once. For example, the sine here is used in two places. One is to the up here, and the other one goes back to here. Now, in the microcontroller programming, you have to remember that calculating trigonometry function takes a lot of time. So it is much better for us, okay, to uh, store the value, sine and cosine value, and then use it for later purpose. All right. So here I will store the sine and cosine value. Let's say I will use underscore sine and double underscore cosine. Okay. So example here, now I can, oh, later. Sorry. So now we will calculate this part. We calculate this part, and then this part is basically equals to error multiplied by cosine, error multiplied by cosine, and then multiplied again by mu2. Mu2 will be around, I need to check my actual code. This way, which one is actual code? This is actual code that I do in the NL5. So for this one, the mu0, the okay, all right. I cannot really, I cannot even read my own code anymore. All right, no problem. So I can directly calculate. All right. So for this one, I hope you can bear with me. So this one will be a little bit like a magic. So I directly obtain the omega. All right, so I will show you how the logic works later. So now I can directly calculate the omega instead of omega equals to um, omega equal plus minus equals to how this value plus the error here, sorry, plus the error from here. So okay, instead of error multiplied by the cosine value here underscore cosine by mu2. All right. So mu2, we can calculate the value of the mu2 here according using this relationship. So we can use Excel here. So here I just put it here. Mu2 equals to uh, omega feed forward square divided by pi multiplied by the damping ratio. So let's say now the omega ff is around 55 hertz. Just take the middle value, make it easy. 2 times pi times 55 square divided by, I forget, divided by 8 multiplied by the zeta. So divided by 8 multiplied by, for because it's for control purpose, so I like to choose a damping ratio of 0.6 or 0.6 multiplied square. Okay, so the new two value is 41,400. Okay, multiplied by mu2, so 41,400. What was it? 66. Okay, and then lastly we multiplied with ps. Okay, so where is it? So basically now we can directly skip all of this and directly obtain the omega here. Okay, and then for this omega, uh, we can obtain the omega with using this integrator. And then, okay, however, one part is still missing. This integrator needs to apply this initial condition, right? So in order for us to apply the initial condition, um, one thing can do, but this is pretty much specific to the QSpice. Is what we can do is we can run it in this line. So basically, in the QSpice, this first part, this if was it exclamation mark and then I don't know how to call this asterisk opaque. This part of the code only run at the very first time you run the simulation. So when t equals to 0, so we can uh, put our how to say this initialization code in here. So for example, so here I can simply number one, I have to declare, I have to define this first, okay, and then I can simply say that instance of the omega equals to 2 times pi times 55. Or how much is it? 2 times pi times 55. 3, 4, 5. Okay, this is also a good programming practice. So if you for constant, just declare the constant here. Pi equals to how much is pi? Equals to pi. Ta-da! Boom. Make it longer. Da, 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 da. Sorry. Boom. Make it longer. La, la, la. Yeah, yeah, yeah. Okay. This is just me being me. Where are you? Where are you? Where is it? Oh, here. Okay, so yeah, whatever this long number. So pi is this long number. So here in the initialization code, I can just write 2 times pi times 2 times pi times 50. That. So we can, this way we initialize the value of the frequency estimation at 55 hertz. Okay, and then next part is we implement this clamping, integrated clamping. Okay, so to do that we can simply omega equals, oh sorry, we can use if here. If omega is greater than, let's say, 2 pi 60, okay, because for this part okay, for the initialization code you only need to run this one once, so it's okay for me to calculate it here, but for this comparator we have to run, so this one it's better for us to pre-calculate what is the value. We don't need to put the multiplication there. So here we can simply say like equals to 2 times pi times 60. Okay, pi times 60. 5. Yeah, I can read this. 408. Oh, okay. 408 equals to 2 times pi times 45. Okay. 408.4. 408.4. Then we can prime it. W equals to 408.4. And then if the value of the double frequency estimation is less than, what was it, 2, then we clamp it to 282.7. Okay, so now we tackle this two part of the code. We can calculate the theta. Okay, so again, theta is just integral of omega. Okay, so theta is equal to, do I already declare this value? Theta not yet. Why this is sine cos? Oh, omega I haven't declared it here. Double omega, double theta. By the way, is there any question or is it over? Okay, everybody can hear me, right? Hello, 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 hello.
Yeah.
Oh yeah, you guys can hear me, right?
Uh,
Can people follow me, or is it overwhelming? Or are you concentrating?
yeah. Sorry, sorry.
No problem. Okay, so theta is just integrator, so the omega integral of the frequency, so omega multiplied by s. Okay, and the next part we have to clamp it whenever the value is greater than 2 pi, right? So we can write it here like this. Oh, yes. If you can use if else here. If theta is greater than 2 pi, I'll just write it here. It's better. 3 pi by 2. Okay, where is it? 2 times. Oh, it's a lot shorter. Okay, I can make it a little. Okay, same. Okay, so pi 2 is like that. It's theta is theta minus pi 2. Okay, so this is how we in why I do not just set if this one happens, why do not I just set into 0? The reason is because let's say okay, pi and 2 pi is a little bit confusing to talk, but let's say that we can talk about degree. So the degree range is from 0 to 300, let's say 60, right? So basically 370, mathematically speaking, is sorry, 370 degree, mathematically speaking, is equal to 10 degrees. And the reason why I do not just reset to 0 is because let's say I detected that the angle is 361 degree. Then if I reset to 0 degree, then these two values are not equal. Okay, these two values are not equal. So this is the symbol of not equal. But if I say this is 361 degree, and then what I did is uh, 361 minus 360, then I will get 1 degree. Then mathematically speaking, these two are equal. Okay, so that's why here the way I reset is by minus 2 pi, right? Okay, and then if this is the 2 pi, so here we get the theta, right? After we get the theta, then we can compute the sine and cosine. Okay, but okay, because in this algorithm we have these two brands, and then for this brands at the bottom here, for the brands at the bottom here, we we use the old cosine to calculate these brands at the bottom. So if I calculate the value of the new sine and cosine here, if I like calculate the sine new value of sine and cosine here, then basically the cosine will use the old value, but the middle branch here will use the new value of the sine, which is I think it's not correct. So what I did instead is just stop here for this branch, all right? And then I will calculate the sine and cosine at the very end of the code. Okay, so basically here, so now we calculate the middle branch here. So for the middle branch, Well, is it? Okay, so middle branch is simple. So we also have an integrator here. Okay. So same like before. So if before we directly jump to obtain the omega, now we also directly jump to obtain the voltage, the voltage estimation. Okay. So variable here, double V K. Okay. I can just write here is the variable V is equals to, this is an integral, right? So basically it's of V plus something 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 times the TS. Okay. And then for this fee estimation here, okay, v is here, so I use the error multiplied by the sign value. Okay, so figure of error multiplied by instance of the underscore sign, the sign that we already calculate properly, and multiplied by the estimated frequency. Okay, let me see. For the omega here, omega is equals to, okay, omega is correct. But in here, there is actually one thing that I missed. So I missed to include this bottom term here that I kind of forget. But it's okay. We will continue writing that one later. So now let's continue on the middle part. Here is the multiplication of error multiplied by sign multiplied by the frequency feed forward. Okay. Sorry, yeah, the frequency estimation. So here I can say instance of omega underscore low pass filter because it's after the low pass filter. Okay. And one, two, three term. Okay, that is the end and multiplied by the sampling frequency. Okay, so yeah, this is the estimation of the a sine wave magnitude. Okay, so now because I just noticed that this the omega estimation is almost correct, not fully, but yeah, almost. So all right, so now we can, so omega is like this. So omega is correct, but for the theta, we need to have this extra branch on the bottom here, right? So this extra branch is basically can be calculated as what is it called? Error multiplied by cosine, and then multiplied by this uh, omega. Okay, so this theta here, I have to multiply this formula as omega plus, so let me see, so this is omega plus all of these terms, so we have to insert the error, insert error, insert error, and then multiply by the cosine value. Okay, instance underscore cosine. Okay, and then we multiply it once more by the estimated frequency with after low pass filter. Okay, so we extend this term quite a little bit for the theta estimation. Okay, so now I believe we already calculate everything. Okay, then as a final thing that we need to calculate is, sorry, we need to calculate the value for the sine and the cosine. Okay, so here we can calculate that instance underscore sine is equals to sine of theta. Okay, and then instance of the underscore cosine is equals to get the sine and cosine, then we can calculate the value
Yes, I
Hello,
can.
hello.
Yeah.
Oh, okay. Okay. How long did my screen disconnected? Do you notice my screen
10 seconds, not
disconnected?
much.
Oh, okay. Okay. Very little bit. Yeah, because luckily I'm using my phone for the voice, so connected, I can still monitor it. All right. So okay. So now I need to write the how to implement the low pass filter in the discrete domain. Before I already explained how to implement the integrator in the discrete time domain, right? So now let's talk about the low pass filter. Okay, so now to explain about this, uh, I only have the WPS, so it's not really convenient to write equation, but I hope you guys can bear with me. By the way, is there any question? Let's just talk about, yeah, whatever you have in mind. Any question? Any question?
No.
So this is the low pass filter equation. 1 multiplied by the S. Sorry. No. Okay. No can means two things oftentimes. Like no, everything is good, or no, I don't understand anything. Which one is which? Okay, so this is a general low pass filter equation. Okay, so typically most in the most common form, you will see that uh, yeah, yeah. It's not very convenient. The most common form that you will see, Okay, but if you want to directly talk about the cutoff frequency, you can directly invert it like this. So S over omega. So this omega will be the cutoff frequency. Okay, function in the Laplace domain. So the next thing we can do is we just mix move the a few things around to do this. Okay, this one is easy. Why? Why is it? Yeah, I don't think it. Sometimes they don't use the same plus y um, and then multiplied by x. Okay, so now here we see that we have this s term, right? So the s in the Laplace is equal. Okay, s is actually same as a derivative, right? So derivative in the Laplace domain, then you can oh magic. Okay, so it means that in the how to say this the discrete time domain, it will be 1 minus c to the power of minus 1, okay, divided by sampling time. Okay, now here I just put it write it a little bit poorly like this. Yeah, so divided by sampling time t. Okay, so it means derivative can be calculated as the current sampling result value minus the previous sampling value divided by the sampling time. Okay, so now we can rewrite the equation a little bit. Okay, so now let's write it down again here, and then so s so it becomes okay y over omega, and then I have to rewrite the s becomes like that. So multiplied by here divided by t, and then this one here is 1 minus z to the power of negative 1, right? So after we look at this, then the next thing we can do is we multiply all the terms with the omega t, so we do not have any denominator anymore. Okay, and then we combine these two terms. So here we will have basically at the end here we will have the let me see how to copy this y minus y is equal to the power of 1 plus y multiplied by omega t divided by omega t. All right. So now, okay, okay, I want to check if my screen is still connected. Okay, good. So now we just need to rearrange the term a little bit. Okay. So how to rearrange it looks a little bit weird. Hmm. Let me see. Let me see. Oh, it's this one. Okay. Oh, why? Okay. This is slightly different than what I used to, right? Why? Let me omega. Mm-hmm. See, let me see. Sorry. How is equal to 1 divided by omega? Divided by omega. S plus omega. Ah, yeah. Okay. All right. Okay. All right. Let's continue first. So basically now we can rewrite the equation. Next we can continue that derivation into, so we move this previous term, the previous measurement to the right. This one becomes plus, and becomes plus because we move it to the right side, right hand side. And so basically now we have this two term here. So this one becomes 1 plus omega t like this. Okay, somebody's outside the figure. Okay, and then now then the last part will be to calculate. So at the end of the equation, what we want is, hey, where are you? At the end of the equation, what we want is this: y equals to this part divided by 1 plus omega t. So yeah, so this one here, this one here is the same. You can move this one up here. Sorry, you can move this one up here, and this one thing down. Sorry, here. All right. So when we are looking at this equation, yeah, we can simply calculate our formula this way. Okay, so here basically means y is equals to some. Here we can divide the value in the programming term in this manner. So y equals to y multiplied by k1 plus x multiplied by k2. Okay, and then sorry, and then here we can calculate the value for sorry, we can calculate the value for the uh, k1 and k2 using this formula, right? So now let's open the Excel again. Sorry, it's here. Let's do this. So k1, and here I have the k2. So k1 is equals to 1 divided by, yeah, well, 1 plus omega 2 times pi times 20 hertz, let's say for the 20 hertz, right? We have the two terms. We have multiplied by the sampling frequency, which is 10 e minus 6. That. And K2 is equals to blah, 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 blah. Okay, omega t. But you can follow this whole equation, or you can simply write 1 equals to 1 minus this. It's the same result. Okay, so I got the wrong thing. So low pass filter is equals to the previous value of the low pass filter, okay, multiplied by k1. What was the k1 value? All right, and then oh, plus the instance of uh, the input of the filter, which is a frequency estimation multiplied by this. Then, and then for the uh, voltage estimation, here I use the 10 hertz. So I need to recalculate the value here. Here it just becomes 10. Then equals to instance of the v underscore LPF multiplied by this value, sorry, plus instance of the v multiplied by, let's just it longer, I don't know. All right, okay. All right, so now after finish the whole algorithm, this is why, okay, all right. So after we finish the whole algorithm, okay, just put it on the right. I need to open this thing, the overall schematic. Now we just need to send the estimation to the each of the ports. So here again, so basically for the okay, so number one is the magnitude, so we can just say instance of the v, that is the v, yeah, v multiplied by 220, okay, and then there is this mac underscore LPF equals to instance of the v underscore LPF times 220, and then there's a DC. DC is equals to instance of the DC value multiplied by 220, okay, because uh, we have to multiply with the normalization factor. So basically here I do not put this for the DC estimation here. I actually for the monitoring we have to also multiply with 220. I forgot to put it here. Okay, and then what's next? So I have the DC, the frequency. Okay, frequency is equals to instance of the omega divided by pi 2. Okay, and then there is this frequency underscore LPF equals to instance of the omega underscore LPF divided by 2, and then there is this frequency, so TH equals to instance of the theta. Okay, now actually normally it's not really recommended to write the program this long without any testing throughout writing, but now we just let's see how it works. Hope there is not much error here. No error. Okay, where is the error? Um, there should be some error from time to time. Okay, it says that the omega LPF is not a member of SPLL, so I forgot to add that member here. So here I have to add this double omega underscore LPF, and then here I also have to add this double voltage underscore low filter. Okay, F6. Okay, new error. Expected that. I often forget to write a few things here. I forget to write this semicolon, and then I try to recompile, and then it complains what the hell is sin and cosine. Okay, so the reason why it has that error is because I forget to include the oh wait, it's so weird. Somebody called me at this time. Include uh, math.h. Oh, I don't know. So suddenly somebody called me. All right. Okay. So once you're connected, now I try to recompile it. Let's see if there is any other error. Okay, created successfully. Okay, so now let's try to run. Then press F5. So, okay. Oh, good gracious, it works right off the bat. Now here, basically now let's to make it a little bit easier to observe. I remove the offset in the sine wave generation, okay, and then we run the whole algorithm first. Right? So this is a sine wave, and then this is the amplitude estimation. Okay, and then here I can also add the sorry, in this one I can also add the DC estimation. Where is it? DC. Okay, DC estimation is set at 0, and then here I can and then I can click Control W to open a new panel here like this, Control C to put the grid here, and then I can just like this, and then I can make a new panel, Control G again, and then I can plot the frequency estimation and then the frequency estimation after the pass filter. Right bang on at 50 hertz. after some like 150 milliseconds. Okay, so now everything is perfect. Now let's try to see what will happen if we add some offset in the sine wave. So here I add some offset, let's say 10 volt. So we run the simulation. And here we see that the magnitude estimation here is still at 155. Sorry, the magnitude, this one is still at 155 for the magnitude estimation, and then the DC offset estimation is right at 10 hertz, which is exactly the same as the number that we insert here. And then, for example, what if we suddenly have an offset right in the middle of the simulation, not from the beginning? Okay, we can also try to add that. So let's say now here the offset is 0. Yeah, this is annoying thing. But here I add a different voltage source. Here I can use a step. What's it? Okay, I can just use pulse. So I can use a pulse. 0 value is 1, and then the delay is just at 0. And then basically here what I will do is I will like how to say this, switch between with offset or without offset, things like that. Okay, so this one is the rise time is 0. I can just 1 nano, falling time is 1 nano, and then on time I can just simply set it as 300 millisecond, and then the period is 600 millisecond. Okay, so now we can rerun this. Oh, sorry, the magnitude of the offset cannot be too small, because if it's too small, we cannot really see the effect. Okay, now we can rerun the simulation. So here we can clearly see that at 300 milliseconds, suddenly I remove the offset. Okay, and then when I remove the offset, of course, all the estimation will may vary a little bit. Okay, and then it go back, and then it can quickly track the offset magnitude, like just like this. Okay, and then when I apply the offset again, it can closely track it very soon. Okay, so yeah, basically it worked much faster than what I expect. Is there any question, or is it too complicated to follow? Hello, hello, hello. Oh, three. Why topic? Press three. Any question?
No, no.
No. If not, then if nobody have any question, then we can finish.
Uh,
So you can ask me different thing as well.
yeah. Hello, Arif.
Hmm.
Yeah, my simulation has done, but I have a little difference in my beginning of the simulation with you.
Mm-hmm. Why is it?
Yeah, I don't know, but
You want to share? You can share your screen
okay.
if you want.
Yeah, can you see my screen?
Mm-hmm. Okay.
Yeah, a little bit difference with your simulation in the beginning.
Can you apply the grid? It's a little bit easier. Oh, okay. Like the transient, initial transient is a
Yeah,
little bit different. Okay. Yeah. See how what is my look like. It's very Maybe you can scroll down to your, yeah, your algorithm.
Yeah.
Maybe you can also try to apply the offset and maybe can more to the accuracy. You can leave for you that track actually. Something weird. My computer suddenly get disconnected. All right.
Okay.
Okay. Where is it? Where is it? Okay. Can you see my screen? Oh, I think. Oh yeah, I can see in my phone. Yeah, people can see my screen. Right. So the other test that we often like to do is we try to test what if we suddenly change the magnitude of the injection, or what if we suddenly change the amount of the, what's it called, the amount of the sorry, we can suddenly change the frequency or we can change the phase. So for example, hey, we don't need this, we don't need this. Okay, so we add one more curve here. Control G, we can add the frequency estimation, frequency, and the frequency LPF. And here I can try to add like the, eh, well, how to do this? Let me see. Oh, I know. I can use a B function. So I can press letter B and then I can make the like the formula for the equation that I want. So for example, here I can write value is equals to uh, 155 times sine of 2 times pi times 50, for example, just to, for the first try. Okay, now I can try to run the simulation. Oh, oh, why where is it zero? Sine, sin, sine,
Sign.
sin, not sine. Should be sin. Let's see. Why is it not making sine wave? Should be making sine wave. Why you zero? Oh, t equals to v. Oh, times t. Sorry, I forget to times multiply by time. Okay, should be multiplied by time. Okay, now sine wave again. Sine wave has come back. So Control G. So now I can plot the magnitude of the low pass filter and then the DC value. If you want, you can also add the low pass filter there. Control G. Here I can add the frequency and the frequency of the low pass filter, and then I can add the theta estimation. Okay, so now I can write a new equation where I can suddenly change the magnitude of the signal after some times, right? So here I can try. So if the time is be if the time is less than 500 millisecond, Then I will go with this one. Okay, and then plus if the time is bigger than, okay, like this, if the time is bigger than 500 millisecond, 500 millisecond, then I will use a much big, like 210. So I can also try to do this. We run the simulation. So we can see that until 0 to 500 millisecond, this is the magnitude. And then suddenly at 500 millisecond, I suddenly change the magnitude to 220, and we can see that the estimation, the new, the corrected estimation takes in, I don't know, like 80 millisecond or something like that. Okay, and then the other thing that I can also try is, for example, I can, number one, put the jumper here, and then I can make the jumper here to next step. And then I can also try, for example, suddenly change the offset, the frequency. So this is 50, right, at the beginning. So I can, let's say here I still here I set the same magnitude if I want. Oh, okay, I can set a different magnitude and also different frequency here. Okay, like this, and they run. Here you can see that the first frequency estimation is at 50 hertz, and then after sometimes after 500 milliseconds, the frequency estimation goes to 60 hertz, and then the amplitude estimation is also tracking closely. Okay, and then if I want to make it a little bit more, to make it a little longer, at this time I'll also introduce like a massive amount of offset. Okay, so for example, here I can add 50. That's not practical actually, because if your measurement offset is up to 50-fold, then you have bigger problem. Sorry. Okay. Ah. Oh, I can just move it like this. Okay. I don't need to see these two currents. Not really useful at all. Here, let's try again. Yeah, so here we see that at this 500 millisecond, three things happen at the same time. Suddenly change the frequency, suddenly change the magnitude, suddenly change the offset, and everything can be tracked pretty accurately. That's it. So, anything to discuss? Is there anything to discuss? Anything want to, or if you guys still
Yeah.
trying to follow this?
Yeah, I can follow it, but just to copy your code.
Sachin disappear.